Hi students, welcome to Practical Science. This is episode 2 and we're going to have a little bit of an exploration into empirical formula. What's one of the favourite experiments that everybody loves to do? Burning magnesium. So let's have a quick look at that one. Here's some magnesium from episode 1. I'm going to see if we can heat this magnesium in order to create a chemical reaction between the magnesium, which we know is an active metal, and the oxygen in the atmosphere. In order to do that, I need to heat it up to start the reaction. You can see the reaction is a rapid reaction. We get this beautiful white powder. This powder is magnesium oxide. You can see that the compound magnesium oxide is very different to the two elements that make up magnesium oxide, the magnesium, the solid metal, and the oxygen from the atmosphere. There's a lot of things that we could talk about in terms of the characteristics and the properties of elements and compounds. But what we want to do today is we want to make it a little bit more mathematical. We want to look at how we can determine exactly how much oxygen has reacted with the magnesium in order to form the magnesium oxide. So burning magnesium is such a lot of fun, but what we want to try and do is we want to see if we can quantify this in some way. That is, to work out exactly how much oxygen is combining with the magnesium in order to form that magnesium oxide product. To do that, we need to weigh the magnesium beforehand. So I'm going to grab a little piece of my magnesium ribbon. I can't use the one that I've already used, so I'm going to use a new, nice, clean piece. So here is my magnesium. This time though, what I want to try and do is I want to try and recover all of that magnesium oxide. So to do that, what I want to do is I want to weigh it, but I don't want to hold it. I'd like to actually contain it within a crucible. So this is a crucible, and what I want to do is weigh my crucible. So my crucible weighs 6.87 grams. So now I'm going to add my piece of magnesium. So crucible plus magnesium is 6.90 grams. Okay, so what we want to do now is we want to heat the crucible with the magnesium. I'm actually going to just ensure all of the magnesium is in there. So to do that, I'm just going to twist my magnesium a little bit. So I want to try, if I can, to get all of my magnesium to react. So I'm going to put my magnesium in there. And I have my crucible lid, which I can place on there to ensure that none of the smoke escapes. But what I want to do first is I want to start to heat it up. So let's turn this Bunsen burner back on and heat it up. So one of the things that we talk about in chemistry is activation energy, which is the amount of energy that a chemical reaction needs in order to proceed. So if we don't supply sufficient energy, then that reaction will not proceed. It's like a hill that the reactants need to get over, have sufficient energy in order to get over that hill, and then the reaction will proceed. So you can see that the magnesium is not going to just spontaneously burst into flames. It needs a certain amount of energy that we've got to add first in order for it to have sufficient energy to then react. And that's what we're trying to do now, just in a more controlled way. So obviously with the ceramic crucible, it takes a little longer to heat up, and it takes a little longer for that heat to transfer into the magnesium, and therefore for the magnesium to rise to a sufficient temperature where it's going to react with the oxygen in the same way that we saw when we put it directly in the flame. So one of the problems you can see with this is once it's going, a lot of that white magnesium oxide powder is escaping. And that's actually going to reduce the mass of the final product. So think about that as one of your potential sources of error for this experiment. I'm going to have a quick look in there. It's looking pretty good. So I'm going to turn my Bunsen burner off. Let's have a look at this product now. Okay, you can see it's pretty much, most of that's reacting. I don't want to weigh it just yet because it's going to be extraordinarily hot. So what we might do is we might have a look at another way of calculating empirical formula. The second way of calculating empirical formula is to again use one of the substances we used in our first episode. So this is copper sulfate pentahydrate. So penta means 5, and if you hydrate yourself, you take on water. So that means there's actual water molecules that are locked up in the crystal structure here. So what we want to do this time is the same thing we did before. We're going to weigh out a certain amount of this particular substance, but this time when we heat it, what we want to try and do is just make sure that the temperature is above 100 degrees, which means the water will boil and it will disappear from the crystal structure. So that means what we should find is this time, instead of the magnesium oxide, which was a product that increased its mass as a result of taking in another element, this one is going to lose mass because we're going to allow that water to escape. So this time, I don't want to put the crucible lid on, I want to leave it off, and hopefully some of that water will escape as steam or water vapor, and we'll find a different mass for this once we've driven all the water off. So we're going to use a second crucible. This one's nice and cold, so I can handle this one. 6.97 grams. And this time, I'm going to tar it, and we're going to add in about 0.5 gram of our copper sulfate. So I'm not going to put about, I'm going to write down exactly what it is. So the copper sulfate pentahydrate, there's an answer for you for later on, is 0.52 grams. So once again, we're going to do the same thing. We're going to come over, turn that off. I'm going to pop that on. I'm going to be very careful because this is still warm from my last experiment. We're going to check how much gas is in there, which still looks like it's okay. So let's set it away. The interesting thing about this particular experiment is we're not going to just drive away some of the steam. You can already see some of that water that is basically boiling in the crystal structure. It's not boiling per se, but what it's doing is it's actually coming out of the crystal structure, which is going to change the appearance of the copper sulfate as well. So these beautiful blue crystals are characteristic of the hydrated form of copper sulfate, and what we're looking for is the dehydrated form, which is the form that has all of the water driven out of it. And you can see some of the steam that's been rising out of the crystal structures that are where the water molecules are locked up. You can see that the color pales, it's almost white. The powder's almost white. So when you say what color is copper sulfate, actually it's pretty close to white. all those beautiful blue crystals have almost all completely lost their color. So that's telling you something about how the water molecules in the structure are interacting with the light that's actually coming into the crystals. And that is why we use a clay pipe triangle whenever we're heating ceramics. So this time I'm going to have to repeat the experiment, and of course one of the important things that we sometimes don't emphasize enough in science is the fact that we sometimes do need to repeat our experiments. Time is always a big issue when you're working through your experiments in the laboratories at school. So we want to make sure that where we have the time to repeat something that we do. So I'm going to repeat it. This time I am going to use a gauze mat as well, just to help spread the heat out. Now obviously gauze mats are much better for glassware because they help spread the heat out more evenly, and I do want more direct heat. But my little Bunsen burner is generating a lot of heat. It's working really well, so I think we'll still be okay. So let's repeat these steps again. So let's turn off our Bunsen burner. We're just going to let that cool and then we'll reweigh it. What we should be able to do now, of course, though, is to reweigh our initial one. Better turn that on first. So our final mass is 6.92 grams. So now that we've got a value for the final mass of our magnesium oxide, so let's weigh our second attempt at the copper sulfate. Just make sure that I turn my electronic balance and pop it on. And my value is 7. Just give it a second because it's bouncing around a little bit. 7.58. So how are we going to do our calculations for our empirical formulas? Well, what we need to do is now we've got a ratio, we've got a mass of the magnesium before we started, and we also have a mass of the magnesium oxide at the end of the reaction, which means that we can subtract the mass of magnesium initially from the final mass of the magnesium oxide, and that should give us the amount of oxygen that was actually taken in the reaction. But the two masses don't really help very much if we don't know the relative mass of each individual atom. So that means we need to look at magnesium, and you'll notice that magnesium has a molar mass of 24.31, whereas oxygen has a molar mass of 16. So we need to take those two into account when we do our calculation for empirical formula. So the first empirical formula calculation that I wanted to do was involving the magnesium and the oxygen. So the key values that I needed to look at were the initial mass of the magnesium, because that's always been there. And so from my results book, I can see that there was 6.90 was the value for the crucible plus the magnesium. If I subtract 6.87, which was the mass of the crucible, then I end up with a mass of 0.03 grams. Now what I noticed that when I finished reweighing the crucible with the magnesium oxide, so the white powder that was in there, then I had a value of 6.92. So subtracting that from my original value means that the gain in mass was 0.02 grams. So that gain in mass we're assuming is from the oxygen that combined from the atmosphere with the magnesium to form magnesium oxide. Now this ratio is just the ratio of masses. In order for me to calculate empirical formula, I need to take into account the molar masses. And that's when I go to my periodic table. So that means that I can look now at the number of moles, and the number of moles is what's really important for chemists because that allows us to make some direct comparisons. So this means I need to divide the mass by the molar mass. Number of moles is equal to mass over molar mass. 0.03 divided by 24.31. And my value here is 1.23 times 10 to the minus 3. And for oxygen, 0.02 divided by 16 equals 1.25 times 10 to the minus 3. Now, hopefully you can see, given that I have basically the same order of magnitude for both of these, that the ratio is very, very close to 1 to 1. That would mean my empirical formula calculation for magnesium oxide would be Mg1O1, or more simply, MgO. Now we express all ionic compounds in this way. We know that they are a crystal lattice, an array with a whole series of magnesium and oxygen atoms. And so we don't try and count them all. What we do is we express them in terms of the simplest whole number ratios. And in this case, that would be 1 magnesium to 1 oxygen, and therefore an empirical formula of MgO. Okay, so let's do our second one. Our second one was a little bit more complex, called the water of crystallization. What we were trying to do is to work out the ratio of water to copper sulfate in the original sample of copper sulfate crystals that we had. So the first thing that I need to do is I need to look at the total mass. So over here I'm going to put total mass. So that was our initial mass. Our initial mass, we had 7.7 minus 7.32, which gave us a value of 0.38 grams. So that was our total. And then our final mass was 7.58. So 7.70 minus 7.58 is 0.12 grams. So our assumption that we're making is that this value is the value of water. So that was the steam that you saw disappearing. And so therefore the copper sulfate must be 0.38, which was our total mass, minus 0.12, which was the mass of the water. So these are the two values that I've used here in order to give me 0.26 grams for copper sulfate. So let's put these values into our equation. So copper sulfate, 0.26, and water, 0.12. As we said before, we can't really compare the proportions of these until we take their individual masses into account. So we need to make a calculation of the molar mass for each of these. So for the copper sulfate, this is a slightly more complicated calculation because the copper sulfate is a compound made from copper, which is 63.55, sulfur, 37.02, and oxygen. And so we'll need to write that formula, CuSO4, and do that calculation. And then sure you'll be aware, water is just made up of oxygen, which is our 16, and hydrogen, which is 1.01. So we're going to use the values from our periodic table, despite the fact that if you have a periodic table that you've been given, you should use those values, including and especially during examinations. When you're given a periodic table, and you always will be, you need to make sure that you're using the masses that are written on the table, because they're the ones that are going to be used in the marking schemes. As we did previously, what we need to do if we're working an empirical formula out is we need to calculate the number of moles, which means we need to divide the mass by the molar mass in each of these cases. So let's do that. So how do I find an empirical ratio? Well, what I want to try and do is, if I can't see anything obvious happening here, then what I want to do is I want to divide by the smallest number. In this case, 10 to the minus 3 in both cases is equivalent. So I have 6 lots of that and I have 1 lot of that. So what I'm going to do is I'm going to divide both sides by this number. So obviously if I divide that by itself, then that's going to be 1. So that would make my ratio, my empirical ratio, pretty close to CuSO4 1 4H2O. So based on my calculations, remember I'm trying to use whole number ratios here. 4.09 is close to 4. Unfortunately, in this case, I can actually check my answer, and you'll notice that this is pentahydrate. So this is 5. Given the values that we have and the equipment that we're using, the fact that we've got such small amounts, I'm fairly comfortable with the degree of error associated with this answer. Yes, it would be nice if this number was closer to 5, but it's on the way to 5, and it's certainly within the ballpark of 5. And hopefully, perhaps if I repeat this experiment again, I might find that I can get something even closer. The fact that there's not quite as much water as I expected could also be a result of perhaps not driving all of the water out there. So even though my powder now looks really white, okay, so if I try and mix that around a little bit, you can see it really looks white. So if I ask you what color is copper sulfate, you'll have to say to me, do you mean the dehydrated form or the hydrated form? Because I hope you can clearly see that the copper sulfate here is actually white. It's not blue at all. Having said that, there may still be some water left in that structure. And if I haven't driven quite enough water out of that structure, then that means that I wouldn't have lost quite as much mass as I should potentially have, which means that my values are going to suggest that there's slightly less water than there actually is. The reality is, each time we carry out experiments in science, there are always errors. There are just always errors. We're humans, so we make mistakes anyway. We're also limited by the equipment that we use, by the measuring devices that we have and their levels of accuracy, and sometimes procedurally by some of the things that we do. We can get impatient and pull a reaction out before it's gone to completion. We're also talking about things that are very, very small, and we can't always see exactly where they're up to in a process. Once again, the important thing about these kinds of calculations is that you know what to do with the numbers. Hopefully in questions that you get during examinations, the numbers will work out to be a little bit more consistent with what you know. So it would be nice, for example, if our calculation worked out to exactly 5 waters instead of 4.09. But I'm incredibly happy at the level of accuracy that we can get with all of this equipment, and just with one quick go here to give you a chance to look at exactly how this process of calculation of the empirical formula goes. One of them we got spot on, the magnesium oxide. The second one we got pretty close. So I think overall we've got some nice results for this empirical formula calculation. I think we've risen to the challenge, and hopefully you now have some values that you can use to practice with. Thanks for watching.